Ni hao ma. If you didn't understand what I just said, you could easily use a voice-to-text translator to understand it immediately. Did you understand what I just signed? If you didn't understand what I just signed, you could easily use a sign-to-text translator, right? No. That's because there are no commercially available sign-to-text translators. Think about that. The 70 million individuals who regularly use sign language as a means of communication cannot talk to anyone who doesn't know sign language. So how would you go about and create a translator for a language that doesn't inherently involve speaking or writing? With a camera and a bit of AI magic. The trick behind it all is a convolutional neural net. A convolutional neural net? Well, what is that? It's actually quite simple. It's used to classify images. Now, it's quite easy for a human to classify a dog versus a cat, for example. But it's a lot harder for a computer to do this. This is because computers don't truly see images. They read it as a full array of numbers. Now, each number corresponds to a pixel value. It can be 0 to 1 for black and white photos, or 0 to 255 for color photos with 3 channels for R, G, and B. And in order for a computer to understand these arrays, it uses a convolutional neural net. Now, a convolutional neural net consists of 3 layers: a convolutional layer, a pooling layer, and a fully connected layer. A convolutional layer consists of a kernel or a filter which passes over the image reading pixel values. It applies weights and biases to those pixel values, sums it up, and puts that new sum into a new matrix. Now, let's say you have a 2 by 2 filter. It's going to be reading 4 pixels at a time. Let's say that the pixel values in those 4 pixels are 1, 2, 3, and 4. Now, let's say the filter multiplies the top left by 2, the top right by 1, the bottom left by 3, and the bottom right by 2. The output is going to be, of the top left pixel is going to be 1 times 2, you're going to get 2. Top right is going to be 2 times 1, you're also going to get 2. Bottom left, you're going to get 3 times 3, which is 9. And bottom right, you're going to get 2 times 4, which is 8. Now it's going to sum all of that, which is 21, and put this into a new matrix. So think about it as sort of a flashlight, which has a very focused beam, and it's passing over the image, allowing you to read it. Now, what is this new matrix that is being created? It's called a feature matrix, and it highlights the most important features of the image. It can highlight edges, it can sharpen an image, it can even blur an image. There's a lot of different filters, and they all do a lot of different things. So that's the convolutional layer. Let's move on to the pooling layer. The pooling layer is a lot similar to the convolutional layer in that it has a kernel called the pooling kernel, which slides over the image, reading pixel values and outputting a value into a new matrix. It's different, however, in that it doesn't apply weights or biases to those pixel values. It can either take the average or it can take the highest pixel value. Now, this is important because it reduces the overall size of the matrix. Now, size of the matrix is very important because it makes training a whole lot easier if it's smaller. That's because a smaller matrix has a lot less weights, resulting in less training to decide what those weights are. Next is the fully connected layer, which is a lot similar to a neural net in that it has connected neurons which apply weights and biases to different values, passes to the next layer, and ultimately give a classification. Now, the input into a fully connected layer is a flattened vector, and the output is put through a softmax activation function, which classifies the image as one of the categories. That's it. That's all a convolutional neural net is. So I use the power of convolutional neural nets to classify the ASL alphabet. The dataset that I used consisted of the 26 alphabets along with space, delete, and nothing. I was able to successfully translate this in real time. Let's take a quick look at the code, and then we can do a quick demo later. So after your images are organized into training and validation folders, it's time to run it through the actual model. As mentioned above, the first few steps are convolutional and pooling layers. So there's 5 steps for these layers. 1 is defining the filter size. 2 is running through batch normalization. 3, running through a ReLU activation function. 4 is a pooling layer. And 5 is the dropout layer. So in the first line, the input size of the image, the number of filters, and the size of the filter is defined. Here we've used 64 3x3 filters, and the input size is a 48 by 48 by 1 image, meaning it's a 48 by 48 image that's black and white. So next we run it through batch normalization, which is basically it reduces the shift of weights, which increases the training speed. So that's the second line. Next is the third line, which is where we're going to be running it through a ReLU function. And what the ReLU function does is it introduces some non-linearity into the system, which allows it to classify high-level things such as images. Next, we're going to run it through the pooling layer, and we've defined this pooling layer as having a 2x2 filter. And we're also going to be using max pooling, which takes the highest value in that 2x2 pixel square, and it's going to take that value and output that into the new matrix. And finally, we're going to run it through a dropout layer, which selects random nodes. So it's going to select 25% nodes in this case, and it's going to drop those out. And that basically what it does is it reduces the net's reliance on one single node and increases the generality of the whole net itself, allowing it to classify not only the training data set and other real-world images. So we're going to do those 5 steps 4 times to increase accuracy, and the only thing that's changing each time we're doing it is the number of filters and the size of the filters. So now we have to move on to the fully connected layer. Before we do that, we have to flatten the image into a one-dimensional vector, and then we can pass it on. So the first step in the fully connected layer is to define the number of neurons. That's what dense is, and we're defining it as 256 neurons. Then we run it through batch normalization, ReLU, and drop out 25% of the nodes. So we're going to do that 2 times. The only thing that's changing is we're going to use 512 neurons the next time. So the output of the fully connected layer goes through a softmax function, which is able to classify the image into one of the 29 categories, the 26 letters of the alphabet, and then space, delete, and nothing. So now we have to actually train the model. And this is where it gets really cool. This is where the CNN comes to life and you really see how it starts to work. So it uses backpropagation to set all the weights, and backpropagation consists of 4 steps. You have the forward pass, loss function, the backwards pass, and the weight update. So the forward pass consists of the image going through the model with random weights and ending up with a random classification. Now this random classification is represented in the loss function, which basically tells you how well your model classifies it. So the higher the worse, and the lower the loss function, the better. So then we have the backwards pass, which identifies which weights contributed to the loss function being so high. Then we have the weight update, which updates the weights such that the loss function is going to go lower, and it updates in increments of the learning rate, which can be 0.01, 0.001. You can set that. Think about backpropagation as sort of proofreading a paper. The first time you write it, it might not be so good. But then you go back and you reread it and you identify the parts that are making the paper bad. And you change those parts, and then it improves the overall quality of the paper. That's a lot similar to backpropagation, because you run it through, it might not be too good, the classification is bad, then you identify the weights that cause it to be bad, and you update those weights such that the classification becomes better. So now let's do for a quick demo. So I'm going to use this webcam right here to translate the first few letters of the alphabet. A, B, C, D, E, F, G, H, I, and J. So as you can see, it was able to translate pretty much all the signs that I use. This is incredible considering it's making a prediction on a hand that it's never seen before. However, this is only just the beginning of using AI to translate ASL, because we're only translating the alphabet, not actually the whole words. I hope that in the future we're able to translate the whole words of ASL, allowing sign language users everywhere to talk to whoever they want to, whenever they want to. Thank you.